Here is a scenario that is happening right now on thousands of developer machines. A senior engineer installs Claude Code, spends the first hour amazed. It autocompletes functions, explains errors, writes boilerplate. By day 3, they are using it exactly like a smarter GitHub copilot. By week 2, they have quietly concluded that the 100x productivity headline was marketing fluff. What they never discovered is that they were using roughly 5% of what Claude Code is actually capable of. The entire 8-step agentic workflow, the part that genuinely compresses sprint timelines, was sitting completely untouched. That gap is not a talent problem. It is a knowledge problem, and it is costing teams weeks of velocity every single month. By the end of this lecture, you will know exactly what those 8 steps are and why skipping even one of them breaks the entire system. Now here is the part that surprises almost every engineer the first time they hear it. If you take 3 Claude Code agents, point them all at the same codebase simultaneously, and let them run without an orchestration layer, your code quality goes down, not up. Merge conflicts multiply. Context windows diverge. One agent refactors a module that another agent is actively extending. You end up with broken interfaces, duplicated logic, and a debugging session that erases every hour you thought you saved. More agents, worse output. That is the counterintuitive truth at the center of everything we are covering today. The reason is not that multi-agent systems are bad. It is that parallelism without coordination is just parallel chaos. The 8-step workflow exists precisely to solve this. And the step most teams skip, step 5, conflict resolution, is the one that makes or breaks the entire pipeline. We will get to exactly why in a moment. Let me be specific about what you will be able to do when you finish this lecture. Because vague promises are exactly what got us into the hype problem in the first place. First, you will be able to spin up a coordinated 3-agent Claude Code system across parallel terminals with a clear task boundary for each agent. Second, you will know how to assign an orchestrator role so that agents share context without overwriting each other's work. Third, you will be able to take a realistic 5-day engineering sprint, feature development, test coverage, documentation, and compress it into under 8 hours of wall clock time. Not by cutting corners, by eliminating the sequential bottlenecks that make sprints slow in the first place. These are not theoretical capabilities. They are the direct output of following the 8-step workflow correctly, which means also following step 5 correctly. The step we are going to pay special attention to because it is where most implementations fall apart under real project pressure. Here is the full map of what we are covering across this series. 8 stages, 6 chapters. Stage 1 is environment initialization. Most people think this is trivial, but the defaults Claude Code ships are optimized for single-agent use and actively work against you in a multi-agent setup. Stage 2 is context seeding. Stage 3 is task decomposition. This is where the orchestrator assigns work boundaries. Stage 4 is parallel execution. Stage 5 is conflict resolution, and I want to flag this right now. The original video that popularized this workflow spent less than 90 seconds on step 5. That is the equivalent of teaching someone to fly a plane and skipping the landing chapter. Stage 6 is integration testing. Stage 7 is iterative refinement. Stage 8 is output verification. Each chapter in this lecture series maps directly to 2 of these stages. Coming up next, we go deep into how Claude Code actually builds its internal model of your codebase, and why that mental model is either your biggest asset or your biggest liability depending on one setup decision you make in the first 60 seconds. Do not skip the next chapter. Here is the thing most developers get wrong on day 1. They treat Claude Code like a smarter chat window. The question, tech question, get an answer, paste the code. That mental model will cap your productivity at maybe 1.2x, not 100x. Claude Code is fundamentally different because it operates inside what is called an agentic loop. Instead of a single request-response cycle, it can read your files, write back to them, execute shell commands, inspect the output, and then decide its next action, all without you pressing enter again. Think of it this way. A standard LLM chat is like asking a contractor to describe how they would renovate your kitchen. Claude Code is the contractor who actually shows up, opens the walls, rewires the circuits, and sends you a report. The 4 pillars that make this possible are persistent context across turns, tool use for calling external functions, direct file system read and write access, and shell execution that lets it run tests, compile code, and inspect live output. Remove any one of those 4, and you are back to a fancy autocomplete. Keep all 4, and you have an autonomous coding agent. But knowing it has these powers is not enough. The next scene reveals why most people immediately hit an invisible wall the moment they try to scale it up. So Claude Code has an agentic loop, tool access, and execution. Now here is the invisible wall I mentioned. Every single Claude Code instance, whether it is your orchestrator or a subagent deep in a pipeline, lives inside a context window. That context window is a fixed token budget. Every file it reads, every shell output it ingests, every message in the conversation history, all of it contains tokens. When the window fills up, the agent does not pause and ask for help. It starts forgetting the beginning of the conversation. In a naive single-agent setup handling a large codebase, you will watch it confidently rewrite a module it already rewrote 3 turns ago, because that earlier work has scrolled out of its memory. This is the hidden bottleneck that kills most multi-agent experiments before they produce anything useful. The fix is not a beggar context window. It is designing your workflow so that each agent only ever needs to hold a small, focused slice of context at any one time. That architectural principle is exactly what the 8-step workflow is built around. And then the mechanism that anchors every agent's context, regardless of how many are running in parallel, is a single file you are about to see. The mechanism that solves the context anchor problem is deceptively simple. It is a plain text file called Claude Code placed at the root of your repository. When Claude Code starts in any directory, it automatically reads this file and treats its contents as persistent instructions that persist across every turn of every agent session. Think of it as the system prompt that you control, version alongside your code, and that every subagent in your pipeline inherits without you having to re-inject it manually. A well-crafted Claude defines the project tech stack, the coding convention agents must follow, the tools that are available, the output formats expected, and critically, the safety guardrails that prevent agents from touching infrastructure they should never touch. This is not optional configuration. In the 8-step workflow, Claude is the single source of truth that keeps in parallel aligned without a human in the loop for every decision. Here is what a minimal but complete Claude looks like. Notice 4 sections: project context, conventions, available tools, and forbidden actions. In the next section, we will see exactly how the orchestrator reads this file and uses it to spawn and coordinate the subagent army. Now that we have the single agent foundation, let us scale it up and immediately confront why naive scaling breaks. Imagine you fire up 10 Claude Code sessions pointed at the same codebase and say all of you, build the authentication module. Within minutes, 3 agents are writing the same helper function, 2 have conflicting opinions on the schema, and 1 has deleted a file another was modifying. This is not a hypothetical. It is exactly what happens without a deliberate hierarchy. The orchestrator SIP model is the mental model that transforms that chaos into structured, parallelizable work. The orchestrator is a single Claude Code instance whose only job is to plan, decompose, and delegate. It never writes production code directly. It reads the Claude MD, understands the full scope of work, breaks it into discrete tasks with clear boundaries, and dispatches each task to a dedicated subagent. Each subagent operates in total isolation. It knows only its assigned task, its allowed file paths, and its expected out format. It does not know what other subagents are doing, and does not need to. The orchestrator is the only entity that holds the full picture. This separation of concerns is what makes 100x speed credible, because subagents run in parallel, and parallelism is the only real multiplier in software development. But parallelism is only safe if agents cannot corrupt each other's work. How exactly they stay isolated, that is the next piece. Safe parallelism requires one non-negotiable rule: agents must never communicate through shared mutable state. No 2 subagents should ever write to the same file at the same time. Full stop. So how do they coordinate? Through a pattern borrowed from distributed systems, shared files as message queues, and interface contracts as the protocol. When the orchestrator decomposes tasks, it also defines the interface contracts upfront, the exact file paths each subagent will write to, the exact data shapes those files must contain, and the exact signals the orchestrator will check to know a task is complete. Subagents do not call each other. They do not share an in-memory object. They write their output to a pre-agreed file path, and they write a completion signal, often just a status JSON file, to a pre-agreed location. The orchestrator polls those status files, and only after all upstream contracts are satisfied does it dispatch the next wave of subagents. This architecture has 3 critical properties. First, it is safe. A crashing subagent cannot corrupt another's work. Second, it is observable. You can inspect the state of the entire pipeline by reading a handful of JSON files. Third, it is resumable. If a subagent fails, the orchestrator can redispatch just that task without restarting the whole pipeline. This is the architectural decision that separates multi-agent demos from production-grade workflows. Now let us make this real by setting up the environment where all of this runs. Understanding the mental model is necessary but not sufficient. You need a physical environment where multiple Claude Code agents can run simultaneously without getting in each other's way. On a Mac M series machine, which is the recommended local setup, Because of its unified memory architecture handling multiple heavy processes gracefully, the setup takes under 15 minutes. Install the Claude CLI via npm if you have not already. Step 2. Install tmux, the terminal multiplexer that lets you run multiple terminal sessions inside a single window, each independently scrollable and addressable by name. This matters because when you have 4 subagents running in parallel, you need to be able to switch between their live outputs without losing context on any of them. Step 3. Create a tmux layout with named windows, one for the orchestrator and one per subagent you plan to run. A standard 8-step workflow session typically uses 5 to 6 windows, orchestrator, planner output, 3 feature agents, and a test runner. Step 4. Configure your tmux prefix in copy mode so you can extract agent outputs quickly without reaching for the mouse. This might feel like yak shaving, but a developer who cannot monitor parallel agently will become the bottleneck in a workflow designed to eliminate bottlenecks. The environment is not scaffolding, it is the cockpit. And speaking of cockpits, there is one more environment layer that most tutorials skip entirely, and it is the one that actually prevents agents from destroying each other's work at the Git level. Here is the layer most tutorials skip, and it is the one that causes the most spectacular failures in multi-agent setups. When 2 Claude Code agents modify files in the same Git repository at the same time, they will eventually produce merge conflicts that no AI is equipped to resolve automatically, because the conflicts are between outputs of 2 AI agents who had no awareness of each other. The solution is Git worktree. A Git worktree lets you check out multiple branches of the same repository into completely separate directory paths simultaneously. Each directory is a full working tree. It has its own files, its own index, its own uncommitted changes, but they all share the same Git object store and history. In practice, this means Agent 1 works in /projects/myapp-feat auth. Agent 2 works in /projects/myapp-feat payments, and both directories are branches of the same repo with 0 file level overlap. When both agents finish, the orchestrator runs a standard git merge or rebase, and because the agents in separate branches with separate file scopes by design, there are no conflicts. The commands are 3 lines. Git worktree add. 2. Specify the path. 3. Specify the branch. That is it. This single technique is the version control foundation that makes the entire 8-step parallel workflow possible without turning your repository into a war zone. In the next chapter, we go from foundations to action. Steps 1 through 4 of the workflow, where you will see the orchestrator spawn its first wave of subagents and watch the parallel execution begin in real time. Here is the single most common reason multi-agent Claude code runs fail. The agents are not hallucinating code. They are hallucinating requirements. You gave them an ambiguous prompt, and each agent interpreted it differently. Step 1 exists entirely to prevent that. You write a spec.md, a structured, machine-readable specification file that defines scope, constraints, file boundaries, and acceptance criteria before a single agent is spawned. Look at the before version on the left. Build a user authentication system. That is not a spec. That is a wish. On the right, you see the after. Explicit endpoints, exact file paths, token expiry duration, error codes to return, and what is explicitly out of scope. The out of scope section is the most important part. Without it, agents will implement OAuth, 2-factor auth, and a password reset flow you never asked for, burning tokens and creating merge conflicts. A good spec.md is the contract every agent signs before it starts. Get this wrong and no amount of orchestration will save you. With a solid spec.md in hand, step 2 is decomposing it into a dependency graph of atomic tasks. The word atomic matters here. An atomic task has exactly one clear output, touches a defined set of files, and can be handed to a single agent without that agent needing to negotiate with another agent mid-run. Think of it like a makefile. Each task declares what it produces and what it depends on. The center of the mind map is your feature. From there you branch into independent task clusters, the database schema, the API handlers, the middleware layer, the test suite. Notice that the schema cluster has no upstream dependencies. It can start immediately. The API handlers depend on the schema. The tests depend on the handlers. This ordering is your dispatch sequence. If you ignore dependency ordering and launch all agents simultaneously, you will watch one agent write an API handler against a schema that another agent hasn't finalized yet. The result is code that compiles, but breaks at runtime in ways that are extremely hard to debug. Map the graph first, then dispatch. Now here is the judgment call that separates engineers who get 100x speed from engineers who get 10x. And it comes down to task size. Tasks that are too large cause agent drift. The agent runs for 3 minutes, wanders off the spec, starts refactoring things you did not ask for, and by the time it finishes you have a 400-line diff you need to read entirely before merging. Tasks that are too small create orchestration hell. You spawn 40 agents to write 40 functions, spend more time managing checkpoints and merges than the actual coding would have taken, and the net gain approaches zero. The sweet spot is what I call the 30-minute human equivalent task. If a focused senior developer would take 25 to 35 minutes to do this task correctly, it is the right size for one agent. That maps to roughly 150 to 300 lines of meaningful output, 2 to 5 files touched, and one clear success condition. Anything bigger, split it. Anything smaller, batch it with a sibling task. This heuristic alone will prevent 80% of the orchestration problems you would otherwise hit in steps 3 and 4. And speaking of step 3, what happens when you actually fire these agents is more surprising than you expect. Step 3 is where the architecture becomes real. You are going to multiple Claude Code processes simultaneously, each in its own terminal pane, each running completely unattended. The flag that makes this possible is dangerously skip permissions. I know that name sounds alarming, and it should get your attention, but in a controlled worktree environment, it is the correct choice. Without it, Claude Code pauses and waits for your approval on every file write. With it, the agent runs to completion without interruption. Pair that with the print flag for non-interactive output and a pipe to a log file, and you have a fully headless agent. Look at the code slide. Line 1 launches agent A against worktree, passing a task file as the initial prompt. Lines 2 do the same for agents B and C in parallel. The ampersand at the end of each line is critical. It backgrounds the process so all three start simultaneously, sequentially. The log redirection on each line, you have a persistent record of every action each agent took. If something goes wrong, and it will, that log is your forensic trail. But raw process launching like this has a serious gap. Let me show you what it is. The gap is context. 3 agents launched with identical system prompts will step on each other's work. Agent A and Agent B will both try to modify the same utility file because neither knows the other exists. This is why agent needs a role-specific context injection in its task handoff prompt. The process has 4 parts. First, you identify the agent's role. Is it the schema agent, the API agent, or the test agent? Second, you declare file ownership. Explicitly list which files this agent may write to and which it must treat as read-only. Third, you inject the current state of shared interfaces. If agent A is consuming a type that agent B will produce, include that type definition as a stub so agent A does not invent its own. Fourth, you set a completion signal, a specific file or string the agent must write when done, so the orchestrator knows unambiguously that the task is complete. This 4-part handoff prompt is the difference between agents that collaborate and agents that collide. Miss any one of these 4, and you are debugging ghost conflicts at 2 a.m. Before you dispatch, set up your terminal layout deliberately, because once agents are running, what you can see is what you can manage. The recommended setup is a 3-pane Tmux layout. The top pane is your orchestrator. This is where you monitor, intervene, and issue steering corrections. The bottom left pane tails the log of agent A. The bottom right pane tails the log of agent B or agent C. If you are running 3 subagents, rotate the bottom panes to show whichever agents are currently most active. The key discipline is this. The orchestrator pane is the only pane you type commands into. The agent panes are read-only observation surfaces. If you start typing directly into an agent pane because you want to correct something, you have broken the orchestration model, and you are back to manual coding. What you should do instead, when you see an agent going off course, is type a steering correction into the orchestrator and let the orchestrator send a follow-up prompt. That discipline is exactly what Step 4 is about, and what most teams get completely wrong. Step 4 is the step that Victor's original 8-step video treated as passive. Watch the agents run, collect the output. That framing is wrong, and it will cost you. The orchestrator is not a spectator, it is an active control loop. Here is what that loop looks like in practice. Every 60 to 90 seconds, you scan the agent logs for 3 drift signals. First is the agent writing to files outside its declared ownership. Second is the agent asking clarifying questions, because in headless mode it should never be asking questions, it should be making decisions. Third is the agent's output token rate slowing down dramatically, which signals it is stuck in a reasoning loop. When you detect drift, you have 3 options in escalating order of severity. Option 1. Send a steering prompt, a short, direct follow-up message that re-anchors the agent to the spec. Option 2. Inject a context reset, summarize has been accomplished and restate the remaining cleanly. Option 3. Kill and restart the agent from the last valid checkpoint. Most engineers jump to option 3 too fast and waste the work the agent already completed. Try options 1 and 2 first. They work more often than you think. The checkpoint file pattern is the reliability mechanism that Victor's video skipped entirely, and I want to be direct. Without checkpoints, a multi-agent run is 1 network timeout away from total loss. Here is the pattern. Each agent writes a checkpoint file at the end of every logical unit of work, not at the end of the entire task, but at each internal milestone. The checkpoint file is a simple JSON object. It's the agent ID, the task ID which sub-steps are complete, and the file paths of all outputs written so far. When you restart a killed or failed agent, the startup logic reads this checkpoint file first. If sub-step 3 is marked complete, the agent skips straight to sub-step 4. Look at the code slide. Checkpoint structure is intentionally simple. You want it to be writable and readable in a single JSON parse, with no dependencies on the rest of the codebase. The resumable runner function at the bottom is only 8 lines. 8 lines that save you from rerunning 20 minutes of API calls. This pattern is not optional for production agentic workflows. It is table stakes. The last dimension of step 4 that most teams ignore until it is too late is cost. Token consumption across orchestration strategies varies by a factor of 4 to 6, and the difference is almost entirely due to context bloat. Look at the table. A naive single long-run agent with no context management will consume 180,000 tokens for a medium complexity feature. The same feature with checkpointed short-run agents comes in at 95,000 tokens, a 47% reduction. Add context compaction, where you periodically summarize completed work into a compressed representation before continuing, and you land at 62,000 tokens, a 66% reduction versus naive. Context compaction is not complicated. It is a prompt that says, here is what has been built so far, summarized in 500 tokens. Forget the raw conversation history. Continue from this summary. The cost savings compound across a full project. A 10-agent workflow running for 2 hours without compaction can easily burn 2 million tokens. With compaction, that same workflow stays under 700,000. At current API pricing, that is the difference between a $10 run and a $30 run. Every single time. And this cost discipline is exactly what makes the integration patterns in steps 5 through 8 economically viable at scale. Here is where most multi-agent workflows silently die. You have dispatched 5 subagents in parallel. Each one did exactly what you asked. The front-end agent built a user per profile component expecting an email field. The back-end agent designed the API returning a user email field. Both agents are technically correct. Both agents passed their individual tests. And yet, when you try to integrate them, nothing works. This is the step 5 failure mode. Not a bug in any single agent, but a collision between agents who were never forced to agree on a shared contract. The painful truth is that the more agents you run in parallel, the more likely this collision becomes. In a 5-agent system, you have 10 possible interface pairs. That is 10 potential mismatches hiding in your codebase right now. The developers who claim 100x speed gains and then silently abandon the workflow. This is almost always why. But there is a structured way to prevent this, and it starts with understanding the exact anatomy of an interface mismatch. The solution is not to slow down your agents. It is to introduce a dedicated arbitration agent whose only responsibility is resolving interface mismatches. Here is how the pattern works. Before any subagent begins work, your orchestrator writes a canonical interface spec to a shared file. Call it contract.json. Every agent is given read access to this file at the start of its prompt. Then, after all subagents complete, the arbitration agent runs a single focused task, compare every agent output against contract.json, and produce a unified resolution. The arbitration agent prompt is deliberately narrow. You do not ask it to fix logic bugs. You do not ask it to improve code quality. You give it exactly one job: enforce the contract. This narrow scope is what makes it reliable. The arbitration agent uses the canonical spec as the single source of truth, not its own judgment about what the code should do. Think of it as a compiler for your agent network. It either passes the contract check, or it flags the specific violation with the exact line and field name. This pattern eliminates the ambiguity that causes most integration failures. But there is one more layer you need before you can trust it. The theory is clean. Let me show you what this looks like as an actual pre-merge check script. This runs in your CI pipeline before any agent output touches the main branch. The script loads contract.json, then iterates over every agent out directory, parsing their exported interface types. For each field in the contract, it checks the type, the name, and the nullability. If any agent put deviates, the script exits with a non-zero code and prints the exact mismatch: which agent, which field, what was expected, what was found. Notice line 7. We are not just checking field names, we are validating the TypeScript type signature against the contract schema. This catches the subtle mismatches that a simple string comparison would miss. The whole script runs in under 3 seconds on a typical project. That is 3 seconds standing between you and a production integration failure that could cost you 3 days. Run this check in pre-commit and in CI. Both, never just one. Because the step that will save you is always the one you think is redundant. Coming up next, once your outputs are integrated, who is responsible for testing them? Most developers treat testing as something that happens after development is finished. With a multi-agent workflow, that sequencing is a trap. By the time 5 agents have finished generating code, writing tests retroactively is almost as slow as writing the code itself. Step 6 breaks this bottleneck by assigning a dedicated test-writing subagent that runs concurrently with your implementation agents. The test agent receives the same contract.json your implementation agents have, and it generates unit tests and integration tests against the contract spec, not against the implementation. This is the critical distinction. When tests are written against the spec, they act as a second verification that the implementation conforms to the contract. When tests are written against the implementation, they just confirm whatever the implementation does, bugs included. The test agent focuses on 3 coverage areas: happy path from the contract, edge cases on every nullable field, and error states for every external dependency. Coverage gaps get flagged automatically. The result is that by the time your implementation agents finish, you already have a test suite waiting for them. The integration step now takes minutes instead of hours. But passing tests does not mean the code is good, and that is exactly where Step 7 comes in. Step 7 is where most developers leave significant quality on the table. After implementation and testing, they send the code straight to human review. But human review time is expensive and slow. Step 7 inserts a self-review loop, prompting Claude Code to act as a critical reviewer of its own output before any human sees it. The key is the prompt structure. You do not ask Claude to review this code. That produces generic feedback. You give it a structured checklist and you tell it explicitly, your job is to find problems, not to validate. Tell it to assume the code has at least 3 issues and to find them. This adversarial framing changes the output dramatically. The checklist covers 6 categories: security vulnerabilities, performance anti-patterns, unhandled error branches, type safety violations, missing input validation, and deviation from the original spec. Each flagged item must include the file path, the line number, and a proposed fix. The output is a structured JSON review report that feeds directly into the next step. The self-review loop typically catches 30 to 40% of issues before they reach human review, which means your human reviewers spend their time on architectural decisions rather than typos and null checks. But here is the uncomfortable truth about where this loop breaks down. Let us be completely honest about where AI self-review works and where it fails, because this is the distinction that separates a reliable workflow from a dangerous one. On the positive side, AI self-review is genuinely excellent at catching syntactic issues, obvious null dereferences, missing error handling on standard patterns, and deviations from the spec it was given. These are deterministic pattern matching tasks, and Claude performs them reliably. But there are 3 categories where AI self-review consistently fails, and you need to build human checkpoints around exactly these 3 areas. First, business logic correctness. If the spec itself is wrong, the AI will faithfully implement and approve the wrong behavior. It cannot validate intent. Second, security vulnerabilities that require real-world context. The AI knows standard injection patterns, but does not know that your specific authentication middleware has a known bypass in version 2.3. Third, architectural decisions. The AI will not flag that your technically correct microservice will create an operational nightmare at scale. These 3 blind spots define exactly where your human gate in Step 8 must focus its attention. Do not waste your human reviewers' time on what the AI already caught. Point them directly at the 3 categories the AI cannot see. That handoff is what Step 8 is engineered to do. There is a seductive idea. The ultimate goal of an agentic workflow is full autonomy, no human gates, no approval checkpoints, just code flowing from prompt to production. This idea will cost you a production incident. Step 8 is not a concession that AI is insufficient. It is the architectural decision that makes the entire workflow trustworthy enough to run at scale. The distinction you need to make is between autonomous zones and supervised zones. Autonomous zones are tasks where the cost of a mistake is low and reversible, generating boilerplate, writing unit tests, refactoring within a module. Supervised zones are tasks where the cost of a mistake is high and hard to reverse, schema migrations, authentication changes, anything touching billing or user data. Your human gate in Step 8 sits at the boundary between these 2 zones. The gate is not a full code review, it is a targeted approval for the 3 AI blind spots we identified in Step 7: business logic correctness, contextual security, and architectural scale decisions. Keep the gate narrow and it stays fast. Make it broad and developers will start bypassing it. The goal is a gate that takes 5 minutes and catches the 10% of issues that could cause a production incident. But a 5-minute gate only works if the handoff document is already written for you. The 5-minute gate is only achievable if the human reviewer walks in already knowing what every agent decided and why. That is what the orchestrator-generated handoff document provides. After all subagents complete and the self-review loop finishes, the orchestrator run final Claude Code call with a single task, summarize everything that happened, and produce a structured handoff document. The document has 5 mandatory sections. First, the original task scope and any scope changes that emerge during execution. Second, a list of every agent that ran, what it was asked to do, and what it produced. Third, every conflict that was detected and how the arbitration agent resolved it. Fourth, the self-review findings, categorized by severity. Fifth, the explicit list of decisions that require human approval, with the AI's recommended action for each. This document becomes the PR description. Your human reviewer reads it in 3 minutes, focuses on the flagged decisions, approves or requests changes, and moves on. For a team of 5 developers, this pattern can reclaim 2 to 3 hours of review time per day. But the handoff document only saves time if it reaches the right people through the right channels. And that last integration is what the final scene demonstrates. The final piece is getting the handoff document to your team without adding manual steps. Here is a Claude Code shell execution script that runs as the last action in your orchestrator workflow. It reads the generated handoff BMD file, formats it for 2 targets, Notion and Slack, and posts both in a single run. The Notion integration uses the API to create a new page in your team's agent run database, tagging it with the sprint, the PR number, and the severity level from the self-review findings. The Slack integration posts a condensed 3-line summary to your team channel with a direct link to the full Notion page and the PR. Notice the conditional on line 9. If the self-review found any warning level issues, the Slack message uses an @channel mention to ensure it is not missed. This is the full Step 8 loop closed. From agent execution to team notification, the only human action required is the actual approval decision. Everything else is automated. You now have a complete 8-step architecture that goes from task to production-ready PR with human oversight at exactly the right points. In the next chapter, we stop talking about the architecture and we look at the actual benchmark numbers. Because the 100x claim is either real or it is not, and you deserve to see the data. Let's stop talking about theory and look at actual numbers. We ran controlled benchmark tests across 3 real task categories: writing boilerplate keyword endpoints, generating test suites for existing modules, and producing API documentation. Each task was timed under 3 conditions: a single senior developer working alone, a single Claude agent with no orchestration, and the full 8-step multi-agent workflow. The methodology was strict: same codebase, same acceptance criteria, tasks randomized across sessions to eliminate familiarity bias. The numbers are surprising in both directions. Some results exceeded the 100x claim, and others fell short in ways that matter. Let's break down exactly what we found, because the pattern tells you something critical about where to deploy this workflow and where to leave it alone. The raw data is only half the story. What's hiding behind these averages will change how you plan your next sprint. Here is the honest verdict on the 100x claim. The number is real, but it is not universal. For mechanical, well-defined tasks like boilerplate generation, test scaffolding, and documentation, the 8-step workflow consistently hits 50x to 100x speed gains. The reason is structural. These tasks have deterministic outputs, minimal ambiguity, and the orchestration overhead is tiny relative to the work volume. But now look at the other end of the spectrum: complex architectural decisions, designing an auth system, refactoring a distributed service boundary, evaluating database schema trade-offs, drop to 3 tanks to 10 tanks gains at best. Why? Why? Because the agents spend most of their cycles resolving ambiguity that a human in a single conversation. The coordination cost starts to dominate. So the real skill is not learning to run the 8-step workflow, it is learning to recognize which tasks deserve it. And the decision rule is simpler than you think, but most teams get it backwards. Now let's be brutally honest about when the 8-step workflow is the wrong tool entirely. There are 3 categories of tasks where running the full agent pipeline actively wastes time and money. First, one-off exploratory spikes. If you are trying to figure out whether something is even possible, the overhead of spinning up coordinated agents to answer a question you could answer with a 2-minute prototype is pure cognitive and financial waste. Second, highly context-dependent legacy fixes, bugs that require deep institutional knowledge that no agent has access to, where the specs AMD would take longer to write than the fix itself. Third, tasks under 2 hours of total human effort. The orchestration setup, context loading, and review cycle for a trivial change will cost you more time than just doing it. The ROI threshold is real. Use this checklist before you commit to the full pipeline. it will save you more hours than the workflow itself. And this brings us to the uncomfortable truth about what most teams do wrong before they even start the workflow. The most common mistake teams make after learning the 8-step workflow is immediately asking, can we add more agents to go even faster? The answer, backed by real data, is almost always no. And here is the precise reason why. Agent coordination follows a curve that looks deceptively like linear scaling at first. Go from 1 agent to 4, and you see real gains. Go from 4 to 8, gains slow down. Go from 8 to 16, and something alarming happens. Total task time starts increasing again. This is agent sprawl, and it is the distributed systems engineer's old enemy, Brooks's law, wearing a new mask. Every agent you add creates communication channels that scale quadratically. With 8 agents you have 28 coordination pairs. With 16 you have 120. The orchestrator's conflict resolution load, the context synchronization overhead, and the merge complexity all compound. The optimal 8 count for most real-world tasks sits between 4 and 7. Beyond that, you are paying coordination tax on work that a tighter team would finish faster. But agent sprawl is the second most expensive mistake. The first one is something that happens before you write a single line of specs KMD. Let me show you the most expensive 5 minutes in this team's engineering history. They'd add Auth2 authentication to their platform. They wrote a specs KMD in under 5 minutes, basically one paragraph. It said, add authentication support Google and GitHub login, keep it secure. That was it. No interface contracts, no token storage specification, no session management decisions documented. They spun up 3 parallel agents on step 3. 40 minutes later, Agent A had built a JWT-based system storing tokens in Redis. Agent B had implemented session cookies with PostgreSQL persistence. Agent C had gone with a stateless OAuth2 flow using only client-side tokens. All 3 implementations were internally correct. All 3 were mutually incompatible. The merge conflict was not a technical problem. It was a spec problem that had been laundered into a technical problem. The spec-backed AMD is not a formality. It is a precision instrument. Garbage in, 3 incompatible auth systems out. The rule is simple. Every interface decision, every storage decision, every contract between agents must be locked in the specific AMDA before step 2 completes. Skipping that step does not save time. It multiplies rework. And the final anti-pattern is the one that gets teams fired. The final anti-pattern is the most dangerous one because it feels like trust. Some teams, after getting comfortable with the 8-step workflow, start removing the human gate checkpoints steps 4, 6, 8. Full autonomy. The agents run end-to-end, ship on green CI. It sounds efficient, and for staging environments with strong rollback, it can be. But we have documented 3 production incidents directly caused by removing all human gates. In one case, a fully autonomous agent run correctly past all unit tests, correctly passed all integration tests, and then deployed a database migration. The column was still being read by a production microservice not covered by the test suite. The CI was green. The column was gone. 40 minutes of downtime. The responsible autonomy model keeps humans in the loop at exactly 3 points: after spec finalization, after parallel build completion, and before production deployment. These are not bureaucratic checkpoints. They are the 3 moments where agent context is most likely to diverge from real-world state. Remove them, and you are not running a faster workflow. You are running a faster way to reach a production incident. The good news is that the action plan in the next chapter tells you exactly how to configure these gates for your team's risk tolerance, starting today. You just watched 5 chapters of theory and benchmarks. The only thing that separates you from someone who actually 100x faster is what you do in the next 30 minutes. So let's cut straight to it. You need exactly 3 files to run your first multi-agent workflow: Claude Code, SpecMD, and an orchestrator prompt. Claude MD is your agent's constitution, defines role, constraints, and output format. SpecMD is the single source of truth for what you're building. No spec means no alignment, and misaligned agents are worse than no agents at all. The orchestrator prompt is the controller that hands tasks to subagents and collects results. Copy these 3 templates right now, drop them into your project root, and you will have your first 3-agent pipeline running before this video ends. But here is the part most people skip. And it is the reason their first attempt fails completely. Nobody masters the 8-step workflow on day 1. And you should not try. The engineers who burn out on agent workflows always make the same mistake. They attempt the full orchestration before they understand how a single agent actually behaves under pressure. So here is the proven 3-phase adoption ladder. Phase 1 is single agent mastery. Spend week 1 running 1 agent on 1 well-defined task. Learn where it hallucinates. Learn what spec detail it actually needs. Phase 2 is 2-agent orchestration. Week 2 and 3, add a reviewer agent that critiques the first agent's output. This is where the quality multiplier starts to appear. Phase 3 is full 8-step deployment. Week 4 onward, you layer in the complete pipeline with parallel execution, human gates, and automated validation. Each phase has a concrete exit criterion. Do not move to the next phase until you hit it. Follow this ladder, and the 100x benchmark you saw in the last chapter is not a ceiling. It is your starting point. And in the very next scene, we are going to in the 3 principles that make all of this stick. Let's compress everything from this entire lecture into the 3 principles you must never violate. All 8 steps, from spec writing through final human gate, are just expressions of these 3 ideas. First, spec clarity. An agent without a precise spec is not an autonomous worker. It is an expensive random number generator. Every token of ambiguity in your spec becomes a bug in your output. Second, role isolation. Agents that do too many things become unpredictable. One agent, one responsibility, one output format. That is the rule. The moment you ask an agent to both implement and review its own work, you have lost the quality multiplier entirely. Third, explicit human gates. Automation without checkpoints is not speed. It is technical debt moving at machine velocity. Place a human decision point at every irreversible action and every context boundary. These 3 principles are the reason the 8-step workflow survives contact with real production code bases while other approaches collapse. Now, there is one capability we have not touched yet, and it changes the power of this entire system by an order of magnitude. Here is the honest truth. Everything you learned today, the 8 steps, the 3-phase ladder, the spec templates, that is a complete working system. You can ship with it starting right now. But there is a ceiling. Every agent in this workflow is still operating with the context you manually hand it. It cannot reach out to your live database, your internal API docs, your company's design system, or your CI pipeline results. That ceiling disappears the moment you connect MCP, Model Context Protocol, to your agent workflow. MCP lets your agents pull real-time tool context, live schema introspection, API responses, test runner output, and more, all grounded in your actual system state, not a stale spec file. The next video in this series shows you exactly how to wire MCP tool integration into the 8-step workflow, and the benchmark numbers shift dramatically when you do. If the 100x result surprised you today, what happens in the next video will make you rethink what a small engineering team is even capable of. Subscribe and turn on notifications. You do not want to see those numbers secondhand.